All right, so welcome to the last session of this workshop. Final speaker, last but not least, Volker Schomerus, who will tell us about Supergroup Chern-Simons theory.
Okay, thanks a lot for the invitation to this meeting. I would have loved to come to Heidelberg again, but unfortunately, hybrid life is sometimes as complicated as hybrid conferences. So I had some physical meetings in Hamburg midweek that made it impossible to come. So I hope there will be another opportunity soon. So yeah, I decided, I mean, some of you may know that sort of in the last few years, I've spent most of my time thinking about conformal symmetry in higher dimension and the higher dimensional bootstrap. And I saw sort of the program for this meeting. I decided, though, to talk about a different topic, something that is based on work in progress, mostly with Nesla Agay, Asad Gainudinov, and Mikhail Pankiewicz, and Nesla actually is also here virtually. So, and this work is devoted to supergroup Chern-Simons theory. So there's one paper out, but sort of most of what I'm talking about today is work in preparation. Now, I think in this, so sorry, there will be a slight lag between the slides, I believe, and the main talk that has some technical issues here. I hope it's not too bothersome. So I think in this audience, I hardly have to motivate why we can think about, should think about Chern-Simons theory. I think it has been mentioned in many, many talks. So we all have different reasons to study this. Of course, initially, I think back in the 90s, the primary reason was to study topological invariance of three-manifold and links. That's still an important reason. There's an important link to two-dimensional conformal field theory, particular Westermino-Novikov-Witten model. So that alone is already quite a lot, but there's also other deep relations which are maybe not as well known. The modular space of flat connections is also an incredible host of integrable quantum systems or even super integrable quantum systems. That's a very interesting subject, and also there's deep relations with representation theory. So again, there's many, many reasons to talk about Chern-Simons theory. And again, that's, I don't think I have to dwell on that too much in this audience. Now, the next topic in my title says that I want to study Chern-Simons theory with gauge supergroups rather than ordinary gauge groups. And so here, let me also give a little bit of motivation, although again, I can just basically remind you of some of the main themes, in fact, at this meeting. Like one thing that maybe wasn't the main theme is that, of course, there was many reasons to study Westermino-Novikov-Witten models with supergroups. That was known for a long time in condensed matter, but also with ADS-CFT, there was more motivation, particularly for ADS-3, to study these things in the string theory community, and that kind of relates, of course, to Matthias' talk. And so we spent a lot of time, in fact, also with Thomas Kreutzig, who's one of the organizers, and Thomas Queller, Salur, Kandu, to develop sort of Westermino-Novikov-Witten models for supergroups about 10, I say, almost 15 years ago. Now at this conference, there's another theme that also brought in sort of supergroup Chern-Simons theories. Namely, it was, of course, known mostly due to work of Witten and then Witten, Kapustin, Solina, Mikhailov-Witten, that, I mean, you can realize Chern-Simons theory, let's say in N=4 super Young-Mills theory at boundaries, which correspond in the brane picture to have like a stack of 3 branes ending on the NS5 brane. Now that gives sort of ordinary Chern-Simons theory with ordinary groups. But then if you have, like in this picture, if you have another stack of branes, so you have here a stack of n branes, D3 branes ending on this 5 brane, and here another stack of M or L in this picture, L D branes ending from the other side. In fact, then, as was pointed out in particular in the work of Mikhailov and Witten, you actually get Chern-Simons theory with super gauge groups. In this case, in the simplest case, GL LN. Okay, and so I've copied here this full picture because it kind of is a bit of landscape of this meeting. So we have had quite a few talks actually on this corner here in the center. And I will not talk about this in particular talk by Thomas. He has explained this picture before, and then also by Naoki and Drazon. And I will talk about this line here mostly. Okay, good. So I hope that you are sufficiently curious to study Supergroup Chern-Simons theory. Now let me talk about how I want to do this, and then maybe briefly about why I use this technology, except that I know it very well. So I will use what's called combinatorial quantization of Chern-Simons theory in this endeavor. And so this combinatorial quantization is some technology that framework that we developed with Farah Grosse and Alexeyev back in the 90s. And it was based on work of classical work, instead of classical physics of Volker and Rossley. So the moduli space of flat connection is, of course, an ordinary nice phase space. Okay, it has singularities, but it still is a very nice phase space with a nice Poisson bracket. And of course, there's an interesting problem of quantizing that. And what we proposed at the time is that one can actually quantize this by some sort of exact lattice quantization. So we introduced some lattice gauge theory with the peculiar feature that the connections on the lattice were actually not taking values in a group. So holonomies were not group valued, but quantum group valued. And quantum group means there was some kind of deformation of a group coming along. Now, so Q deformation of a group coming along. And then we developed this kind of quantum group gauge theory. And in the end, showed that when we look at the algebra of gauge invariant objects, that we would recover sort of the quantization of the modular space of flat connections. And so the slogan of this is sort of, in this case, Q deformation actually led to quantization. So Q deformation in the non-observable sector, when you study all the lattice connections, once you descend to the observables, it's just ordinary quantization in the standard sense. And now, although sort of this has not been kind of rigorously, I would say, established that it's really a quantization in the sense of, well, deformation quantization or things like that, what we have been able to show at the time is that the combinatorial quantization of Chern-Simons theory, the way we designed it, provided a Hamiltonian formulation of Reshetikhin-Torayev theory. And that, of course, is, I think, generally accepted to be the same as Chern-Simons. So we did this for, of course, at the time for compact bosonic groups, and then after other people extended that for non-compact group and non-unitary setup. So why do I choose this framework here? I think there's two reasons. In fact, one goes back to Owen's talk yesterday. He already explained a little bit of the spirit of factorization homology. So it turns out that this combinatorial quantization in some sense provided maybe the first really concrete example of this framework of factorization homology, as was noticed by Ben Spinors here and Jordan some decade ago, actually a little less. And so in this factorization homology actually has been used quite profitable to even prove some important theorems. So that's sort of motivation on the math side. So I think this quantization framework is particularly nice because, again, it relates to some of these modern developments and to think about quantization of local theories. And we'll see a little bit more of the spirit that Owen talked about yesterday as I proceed. Another reason for more from the physics audience, who I'm not sure is existent, but still mention it, is that, of course, in the context of quantum computing and fail-safe quantum computing, there has been a lot of attention in the last few years on understanding topological phases of matter. And there's some interesting models that do this. There's in particular sort of the first one, Kitaev's toric code. That's sort of one of the first examples that already provided very interesting state spaces, a space of ground states for your quantum computer. but not enough gates somehow. And then it was generalized to Kitaev models, which had solved this problem that you get enough gates to build your interesting quantum computer. And there's an equivalent set of models that is not very much discussed by many people. That's Levin-Wendt stringnet models. And so these models are known to be Hamiltonian formulation of Turayev-Virov theory. And so probably many of you know that Turayev-Virov theory is in some sense a square of Reshetikhin-Turayev. And so not surprisingly, these two topics are closely related. These string network models of Levin-Wendt actually correspond, are particular examples of this combinatorial Chern-Simons theories when you choose the gauge group to be a double, a Drinfeld double. So this should just give you sort of two reasons. So these are both developments that are very actively researched right now, and in some sense both make contact in particular to this combinatorial approach to quantization. That is, combinatorial really means sort of putting things on the lattice, gluing things from kind of boring degrees of freedom in some sense, but making something interesting out of it. All right, so that brings me now to the outline of results. So I will show you now that this combinatorial quantization that again was initially discussed for or developed to do compact bosonic groups, it can actually be nicely adapted to the quantization if you have gauge supergroups. And of course, you're now all experts. I mean, even those of you who have come to this conference without being experts in superalgebras, you know now that the fun with superalgebras is really that their representation theory is non-semi-simple. There's lots of interesting things that happen. And we have seen just in this beautiful talk this morning by Torsten, I mean, some of these things. So, so I'll show you that in fact, the combinatorial quantization can be very nicely adapted to deal with gauge supergroups. And that uses to some extent, of course, some twists of the story. So it's, you have to present the story slightly twisted to how we did this in the 90s. And in fact, the main twist was invented sort of in this context of factorization homology. I'll maybe point that out again. But then in the end, we will get for any choice of supergroup or superalgebra, any deformation parameter Q, which you can think of H bar. So it's kind of a continuous parameter. And any integer G, which is a genus of a surface, and any number of points, which for reasons that we can call n-1. So for two integers, any Lie algebra and any parameter Q, you obtain a well-defined set of algebras, which have a, so this is the observable algebras of Chern-Simons theory, and these have a very rich representation theory, which is inherits all the richness, I would say, from the richness of the superalgebra. And that again, you have seen in talks of very interesting. So my plan is relatively simple. In the first part, I will talk about combinatorial Chern-Simons theory. I'll give sort of a modern review of this story, which takes into account sort of the way people rethought it in the context of factorization homology. And that will allow me to, so this is of course already adapted then to treat non-semi-simple cases and graded algebras, so even for superalgebras. So I'll discuss how to construct observables states, so how to define these algebras, how to construct representations thereof, and also to obtain mapping class group representations. And then in the second part, I'll look at one example, which is really the first example, namely with the supergroup GL11. The advantage is that it's actually relatively easy to do computations. Still, it's some of the richness is already there. So it's a good, especially for the physicist, a very good first example to look at. But I think if you take this example together with today's talk in the morning by Torsten, you will start to get a feel for how rich the study of these new algebras actually is. So that's the end of my introduction. Are there any questions? Not the case. So I'll talk, as I said, now mostly about what this combinatorial quantization actually is. So this slide well, in this talk, I kind of assume that everybody is somewhat familiar with what a Hopf algebra is. I'm actually not sure it's true. I cannot see your heads and don't know whether you're nodding or shaking or sleeping. So if you do not know, then it will be certainly slightly a little harder to follow, but not impossible. You just have to be a bit more impressionistic. So I don't want to go through all the definitions of what that is. So roughly, what I do on this slide is I give you the main ingredients of the construction. So there's two ingredients in gauge theory, right? You need gauge transformations. So some kind of algebra that generates your gauge transformations, and then you need the holonomies that you put on the links. And that's basically what I describe on this slide. So the gauge transformations now form, first of all, an algebra of gauge transformations, local gauge transformations. So we kind of put many of copies of this together. They actually form a Hopf algebra. So you can think of this G as, I mean, the simplest example would be a universal enveloping of a Lie algebra, and then you can Q deform that, or super Lie algebra can Q deform, then you're here. And then you need a bit of extra structure in order to make the whole construction work. So you need some kind of R matrix, some representation of the braid group through elements in G tensor G. And you need some technical conditions. So this has to be factorizable, and there has to be a Riemann element so that these properties are satisfied. Again, there's usually a long list of axioms that goes along with that, 2 pages, which I don't want to give you here. I hope that roughly you know, and if not, can think of just sort of deforming a universal enveloping algebra for the algebra. So this is an algebraic structure that, if you're more familiar with categories, that would go along with modular tensor categories. This kind of representation theory of this algebra would be a modular tensor category. So that's one element, and that will give us our gauge symmetry as we proceed. So the second ingredient is now the holonomies. So we want to put something that looks like holonomy, an integrated connection along a link or a small curve, which you can think of a link in the lattice. And so, so these things are typically in gauge theory would be just group valued. And if you go sort of Q deform, then it becomes quantum group valued. And so it's defined rather than sort of an algebra of commuting functions on a group, it's an algebra of braided commuting functions. So the typical example of this is really a quantum group, which is a Hopf dual of G. It turns out that there's another interesting deformation of the algebra function, non-commutative deformation of the algebra functions of the group, and that's called a link algebra. There's only a tiny, so the quantum group algebra would be without this prime, and this link algebra has a prime there. So it's a twisted version of the quantum group algebra. It's anyway, it's some non-commutative algebra that deforms in a way the algebra of functions on a group. Now, you can deform that in many ways, but what's special about this deformation is actually it preserves the symmetry. So you know a group has a symmetry on the left and right invariant vector fields, or left and right translations. And this deformation, this Q deformation described by these equations, whether you understand them or not, doesn't matter, has one particular property. It actually preserves these symmetries. So you still have a left and right action, this time of this quantum deformed gauge symmetries or symmetry. So you have some action on the left and some action on the right and some precise term which is described here. So that's kind of special. So the quantum group itself also has this property that it preserves too. So this is just another deformation of the quantum group algebra that has this property. And now with these ingredients, we can start sort of to have fun. So we choose now some Riemann surface, our favorite Riemann surface sigma. And so we will actually choose one that has one disk removed. And there's this one twist that somehow in the story that was invented in the sort of factorization homology story. So you'll see later that this, especially in semi-simple context, is actually a nice way to think about this. So, so you have, you take a Riemann surface of genus G with one disk removed, and you now put a graph on that surface with a vertex set, which I call V, and an edge set, which I call E. And so now what we do is, so we will take for each edge of this graph, we will take one copy of our link algebra, and for each vertex, one copy of our gauge symmetries. And now the fun is kind of, you have to put them together in a consistent way so that you don't break gauge symmetries. And that way of putting things together now starts to see the geometry of the surface. So when you have two, so in fact, holonomies, of course, are sort of oriented links, so you can have both orientations. So it turns out that the holonomies for the opposite orientation are almost inverse to each other up to this ribbon element. Then if you have two holonomies along links which don't have anything in common, so if I have another link K here, then of course the corresponding holonomies should just commute. That's consistent with all the symmetries. However, when the two links have one point in common, like in this picture here, this X point in common, then if they would commute, you would break the gauge symmetry. So you can't make them commute. You have to make them braided commute. And so you get some kind of relations of this type, okay? And so you now see that, I mean, when you kind of put your whole lattice over the whole lattice, you will have at each vertex some interesting braided commutation. In order to make that really well defined, you actually have to put a little cilium. So you have to take this cyclic order that you have at each vertex and make a linear order. In the end, the constructions won't depend on that just. But so the main lesson is somehow, in order to make an interesting gauge theory, I mean, this is really the point where you marry sort of some boring algebra, these elements, quantum group algebra, or this link algebra, and the surface geometry. In order to get that all right, you somehow get this interesting local braiding, and that is what kind of brings in all this nice geometry. And that's really where you should think of this whole spirit of factorization homology. So when you introduce these type of relations, you can actually check that it preserves this algebra. So you can construct some huge algebra generated by the components of all these holonomies, very non-commutative. And you can check that it preserves gauge transformations, local gauge transformations of all the vertices. And so since it does that, you can actually define an action of this gauge group, so the product of all these local gauge symmetries, make it act on this graph algebra, on the space of functions on quantum lattice holonomies, and you can prepare an algebra of observables, so gauge invariant quantities. And this actually turns out to be independent of the choice of cilium, so you can write this as just a function of the graph, in fact. Now it turns out that it's actually does not even depend on all the features of the graph. I'll comment on that in a second. Any questions at this point? Okay, let me talk a little bit about these graphs. So now we have, in some sense, introduced this algebra that I was advertising before. That's a definition of this algebra. There's a few things that are useful to know about them. So in particular, so I've defined them at first when I wrote the relations only for graphs that have no multiple links between two vertices and no loops. But that's something that you can easily get rid of. It's just convenient if you want to write it. So if you take two link algebras connected by a vertex, then the graph algebra associated with these two links, you see this is some non-commuting copy of two link algebras. When you take the subalgebra of GX invariance, it actually turns out to be isomorphic to the link algebra along this one link without this intermediate vertex. And that allows you, of course, now to also define a graph algebra for multi-links. So if you have, for instance, two links connecting two vertices, you can just, so this is a multi-graph, you can just put an extra vertex here and then G invariance with respect to that. So this is now no longer multi-graph, so it's a graph of the type that I had in the previous slide. And so a subalgebra of this graph is then the one with the multi-link. Similarly, you can do this for loops. So even if initially you don't have a graph with loops, you can just have a loop formed from, I mean, if you have a loop, you can just introduce two extra vertices and then look at the subalgebra of this three-link algebra, which is invariant under these two gauge transformation in these 2 points. And that gives another interesting algebra. It's called the loop algebra. You can actually work this out, what it looks like, and it turns out it's isomorphic to the Hopf algebra that you started with. So it's a G. So that's something you can check. it needs to be proven. It's not maybe not obvious, maybe for a physicist a little more than for a mathematician, but for a mathematician they would appreciate that it's a precise statement. So if you have a three-link algebra and take the invariance with respect to these two vertices, you get something that that is isomorphic to G itself. And of course, this algebra also has gauge symmetry with respect to the adjoint action on G. So now it turns out, so this is one thing, you can actually define this algebra not just for graphs, I mean, simple graphs, but also multi-loops and loops and multi-links are allowed. So that's always defined. So now the strongest statement is that it turns out that this graph algebra actually doesn't depend on all the data. That's the sort of topological nature of Chern-Simons. It depends on the choice of the graph only through the genus on which you drew the graph, and on the number of plaquettes or faces of your graph. Okay, and so it's only the combination of number of edges minus number of vertices that matters, not the two independently. So that's again something one can prove. Okay, and so so basically this now allows us to construct this algebra. So again, we have defined this algebra A of observables of Chern-Simons, some kind of complicated non-commutative algebra. The simplest way of obtaining that from the lattice algebra is in fact to take a graph with just one vertex, right? Because what mattered again was only the difference between the numbers of vertices and number of edges. So you can just take a graph with one vertex. It's a minimal graph you can have, and just loops. And you have two loops for each handle and one loop for each facet or puncture. And so what you then get is a very complicated algebra that has, is built up from 2G plus N minus 1 loop algebras, which are put together in some complicated braided way. Okay, and carries an action of the gauge symmetries. And when you look at the invariant subalgebra, the invariant subalgebra is this algebra of observables that we're interested in. Now, this algebra turns out to have a very interesting subalgebra. That's the handle algebra, which is the algebra that's associated to each handle. You see, when you have a handle, you have two loops for each handle, but they come, I mean, the first one goes here, then the second one goes, then the first comes back, and then the second comes back. That's different from having two holes where you have the first one goes and comes back, second one goes and comes back. So there's an interesting algebra, this handle algebra, that is associated to handle, and that actually turns out to be just the Heidelberg double. For those of you who are familiar with sort of Fox algebra technology. Now, our main task is, of course, to construct representations. So we have defined now this algebra, right? So it's well defined, and you can think through it, and everything is well defined. We'll see an example of this later. But of course, we would like to understand what kind of monster we created at this point, and so the best way to understand that is, of course, to understand what kind of representations this algebra has. And of course, what we expect is somehow that it has a representation that has something to do representation spaces with spaces of conformal blocks. So what actually turns out to be very useful in discussing representations is a theorem that we proved already back in the mid-90s, and that is the following. So when you take this braided algebra where you have these 2G plus N minus 1 loop algebras, and you have braided them together, and you tensor them, so this has an action of the gauge symmetry. So gauge symmetry is now just a single gauge symmetry acting at this one vertex. You can take the semi-direct product, so you get an algebra. And this algebra, in fact, within this algebra, you can somehow unbraid in a precise way. So this should remind you a little bit of a Jordan-Wigner transform, which allows you, if you have fermions, to basically attach to fermions some kind of gauge strings. And by doing so, you can actually turn them into bosons. So this is a little bit similar here. So that only works sort of in this semi-direct product. You can actually construct in there commuting copies of the handle algebra, G commuting copies of the handle algebra, and n-1 commuting copies of the Hopf algebra. And so here everything is sort of mutually commuting, and so that should remind you of sort of bosonic thing in this Jordan-Wigner transform, whereas here everything is braided. But again, I mean, this is absolutely crucial, of course, that you extend the algebra to include the gauge transformations, otherwise it wouldn't work. But so now this allows you to actually construct representations. So the way you do that is now you say, well, I need just representations of the loop algebra, well, n-1 copies of the loop algebra, and I need representations of the Handel algebra. So for the loop algebra, I told you loop algebra is just the Hopf algebra G itself. So you just pick whatever representation you like of your original Hopf algebra. So you take n-1 of these representations, and the representation spaces I denote by h01, 0 is genus 0, 1 loop, and pi m is this representation. So you choose any type of representation that you like. So this would be sort of the markings of Wilson lines and Chern-Simons, or if you think of topological phases of matter, that would be sort of the type of the anionic excitations that you have. On top of that, you have to, of course, choose representations of the Handel algebra. There's G copies of the Handel algebra, and what comes in very handy is that you can actually prove that the Handel algebra has only one representation. So it's kind of a really Heisenberg double, so it really deserves its name. Has one representation on the representation space, which is again as a linear space or as a module. It's just G. Okay. So now, so again, I mean, the Heisenberg algebra, this Handel algebra, was consisting of two copies of G, which were put together. So the state space, of course, has only half the degrees of freedom, right? Only x variables, but no p's. So this is basically a space of wave functions coincides with the with G. So it is half. And so now you can actually build a representation. You pick your n-1 representations of G. You pick your, I mean, you don't have any choice with the Handel. You just represent it on G. And so you get a large representation, linear space on which you can now act with your entire, this entire semi-direct product. Okay. So this is the representation space on which this entire semi-direct product actually acts. But the semi-direct product and the semi-direct product, sort of the gauge transformations and the observables are commuting pairs, okay? So that means if you now decompose, let's say with semi-simple first, if we now decompose this space with respect to the action of the gauge symmetry, the observables will act in the multiplier spaces for this decomposition. And now you can already see why this becomes sort of quite interesting when we do this for non-semi-simple case, because as we discussed at length this morning, so when you decompose tensor products of representations of these super algebras, quantum deformed or not, you get all sorts of interesting phenomena in the decomposition. And somehow your algebra of observables acts basically in the multiplier spaces of these decompositions. That's kind of these spaces whose dimensions we tried to compute this morning. So the upshot of this is that you obtain representations of Chern-Simons observables on these multiplicity spaces in the decomposition of this space. Okay, so the representations roughly are labeled by n representations, choice of n representations of G. n-1 we chose when we labeled our punctures, n-1 punctures, and the last one when we decided which multiplicity space we want to look at. Okay. Good. So time. Okay, that's fine. So one of the most important applications, of course, of these representations is that that it gives you, in fact, important for all sorts of applications, be it invariance of three manifolds or quantum gates for quantum computers, is to study representations of the mapping class group of the surface. And so I guess in this audience, everybody knows what mapping class group is. So what's important for us, it's generated by Dehn twists. So you take your surface, you cut it along some kind of cycle, you twist the cycle by 2 pi and then loop things back. That's a Dehn twist. And so you have, for each cycle on the surface, you have a Dehn twist, and these Dehn twists generate the entire mapping class group. So it turns out that basically these Dehn twists, and thereby the mapping class group, you can embed into the algebra of observables that I just constructed. So for each Dehn twist, there's a particular observable in this algebra that is associated to it. And so the way you construct that is as follows. So I told you the Dehn twist, you first take a curve on your surface. Now, of course, we had all these fundamental cycles on our surface. You remember all these green and red and blue things. So any cycle on the surface, also one that just encircles these 2 points, let's say you can write as a product of these fundamental cycles. And so then you can compute the monodromy by taking products of these fundamental monodromies. So that's sort of a quantum monodromy associated to that particular curve. You multiply that with inverse of the rhythm element. Okay. Then you take well, I didn't talk much about this, but about the right integral from that, and you get actually an element in this algebra. And it turns out that this formula gives, and this we proved, yeah, in particular in this non-semi-simple case with Neschler and Assad and Mikal 2 years back, that you get actually a representation or projective representation of the mapping class group in this way through Chern-Simons observables. So the formula also agrees with an earlier formula that we had in the 90s, but that was written for the semi-simple case. And in that case, we heavily used quantum traces. So the challenge was somehow to get rid of the Q quantum traces, which of course made too many things zero in the non-semi-simple case to be interesting. So once you have these particular, so the algebra of observables that we got just constructed, so that's the main claim now, is it contains basically elements which have the same properties or provide a representation of the mapping class group of the genus G surface with n punctures. So I mean, so if you have genus 0, that's just a pure braid group, and then if you have genus 1 and no punctures, it's the modular group. So all these things can be realized through these Chern-Simons observables. So there's a lot of observables in there. And of course, if you combine it with what I said in the previous slide, namely when you represent it on these multiplicity spaces, then you get just representations of the mapping class group, projective representation of the mapping class group on some finite dimensional vector spaces. And so in the semi-simple case, we proved back then that these are the same representation that Puraev-Viro obtained. In the non-semi-simple case, the understanding is that these are sort of this type of Lubachenko-Mujit representations. All right. Good. So this concludes my review of combinatorial quantization of Chern-Simons theory. I hope it was somewhat illuminating. Again, let me summarize what we have done. We have constructed mostly an algebra, a family of algebras, which as input we can use any graded non-semi-simple Hopf algebra, in particular any Lie superalgebra, Q-deformed Lie superalgebra, any Lie superalgebra, any Q deformation parameter Q, which is sort of our H bar, and a choice of 2 integers for any of these choices we constructed in algebra. We also constructed representations of this algebra on linear spaces, and these multiplicity spaces, and the representation of mapping class group that goes along. So all this is the framework. Again, like the way I've described it now, there's no real subtlety in going from semi-simple to non-semi-simple case. Whereas, of course, in the original formulation, that was not so obvious. All right, any more questions? Or any more questions, I should say. Any questions? Because I haven't gotten any questions yet. All right. as you want to get to the end of the meeting. How am I doing on time? It's so fine. So let me show you a little bit what this can look like. And I think this will maybe, of course, some of the formulas on the previous slide look very elegant, and so also very compact. It's fun when you start unpacking them, unfolding them, and see what they look like when you work things out explicitly. And so I'll show that to you here in the case of the GL11 algebra. This is GL11 Chern-Simons theory. So on this slide, I just give you this quantum deformed, the gauge symmetry basically. So the gauge symmetry in this case is quantum deformed GL11. So yeah, you recognize here these two commuting elements, K alpha and K beta. These are the bosonic guys. Okay, so they commute, and then there's on top of that two fermionic guys, E plus and E minus. You see the bosonic guys, the fermionic guys actually commute with the K alpha. That's sort of the diagonal object in GL11, and they braided commute with these K beta. And then the most interesting relation is the relation between the fermionic E plus and E minus operator, which takes this form. And anybody who has seen, for instance, the definition of Q-deformed SL2 recognize, of course, this very typical type of relations that you have. So this algebra here defines an algebra generated by two bosonic, two fermionic elements. So the universal enveloping of this is GL11, and it can be equipped with a coproduct. There's an R matrix, which I write for you here. Of course, you're not supposed to read this now, just to believe me that there's a very explicit formula. I should maybe say that, so there's a parameter P appearing here. So I take the Q here to be of the form, Q to be of the form e to the 2 pi I over P. So P is sort of roughly the level of Chern-Simons theory, and P I choose to be an odd integer to get all the properties that I desire. And so then this is the P that appears in this formula. So then this is the formula for this R matrix that is so important in kind of defining all the commutation relations of the individual lattice connections. This is a formula for the ribbon element, and this is a formula for this right invariant that we use to construct the representation of mapping transport. So all these things are there. And if I had written all the properties that these things have to have in order to be a quasi-triangular factorizable ribbon of superalgebra, you could check that these objects satisfy all these properties. Okay, so it's a very simple example. Now it's simple, but it's already kind of fun to look at. So the representation theory of GL11 and also UQ GL11 is already somewhat intricate. Of course, as we know now, it's not wild. I mean, both these indices are 1, so there's nothing wild about it. It's very controllable. You can classify all these indecomposable representations, but it's already a limited amount of fun one can have with it. So I give you here, so first of all, there's typical representations. So the typical representations, of course, are 2-dimensional. Of course, somehow in a typical representation, you have to represent your fermionic operators, fermionic creation operator, right? That's like a fermionic creation operator. Of course, fermionic creation operator, you can only apply once. Second application gives 0 because it's a fermion. And so you get typically 2-dimensional representations. And the 2-dimensional representations are labeled by some number E that runs from 1 to P minus 1, and some number N that runs from 0 to P minus 1. And so it has kind of two states, which of course, in 1-dimensional representation of the bosonic subalgebra, which is abelian, and then the fermions that go back and forth between them. So the action, if you look at this, the action of the lowering operator, E plus fermionic lowering operator, comes actually with parameter EQ here, and that parameter EQ is given by this formula. And you see if E is equal to 0, then this is actually 0, and you can only go up, but you can never come down. So this is an example of an indecomposable representation. It has an irreducible subrepresentation, but it's not irreducible, but of course you cannot go from any state to any other state. If you're up here, you can never come back. And so, so you see already the first example, if you have never seen anything like this, of an indecomposable representation. So there's, of course, one-dimensional atypical representations, which is just these subrepresentations labeled by n equals from 0 to p minus 1. These are one-dimensional representation, e is equal to 0. But there's also interesting higher dimensional representations, which in fact, maybe most interesting, most important for us in particular, is denoted here. It's a four-dimensional indecomposable representation. That's, in fact, in technical terms, the projective cover of this irreducible atypical representation. And the way such a representation looks like is that you have a state up here. It says E equals 0 and n quantum number is n. With the fermionic operators, you actually can go this direction to n plus 1, or this direction to n minus 1, and then with E plus, so E minus, of course, you cannot apply again, but E plus, you can apply, you can get here, and E minus, you can get here. So that's an indecomposable representation. You can write on really sort of a matrix form of this like I did before. And it's actually very easy to create this representation. For instance, if you take two typical representations and have E, one with E, the other one with minus E, and you take the tensor product, you will actually get a four-dimensional representation, right? Tensor product of two two-dimensional gives a four-dimensional representation. And that one is this indecomposable representation, such an indecomposable representation. So it cannot be decomposed into subrepresentation. Anyway, so again, this is when you have a typical representation to opposite E charge tensor to each other, otherwise it decomposes. Okay, so that is a crash course in representation theory of GL11. And so now we can put this together and try to understand what this now all implies for the representation theory of our Chern-Simons observables. So I'm wondering where I should start. Maybe let me start here. So let's first consider the case where we have a genus 0, and we put just punctures, an increasing number of punctures on our surface. The punctures we label with some typical representations, let's say E1, N1, E2, N2. So that is basically a representation. The Wilson line is in that punches the surface. And so according to what I told you before, what you have to look at is if you can construct representations is basically, so there's no Handel algebras because it's genus 0. So you just have to take a tensor product of two representations, in this case, typical representations of UQGL11. And so you can take this tensor product, and of course, generically, this tensor product will just be a sum of two typical representations. So it's four-dimensional, and generically, it's a sum of two typical representations. That is, if E1 plus E2 is not equal to 0. So you just get these two representations, and there's the trivial multiplicity spaces. So in this case, you just get one-dimensional representation of your algebra of observables for the two punctured surface sigma with this disk removed. But if you have three punctures, then already it gets more interesting. If you have three punctures labeled again by three typical representations, you can work out the tensor product. And in this case, you get three is, of course, an 8-dimensional representation that decomposes into four two-dimensional representation, and one of them appears with multiplicity 2. So in this case, you start to get representation with interesting multiplicity. And again, these multiplicity spaces now become the representation spaces for your observable algebra. In this case, that would be the pure mapping class group, because we are in the genus 0 situation. And so, and of course, the formulas that I gave you really, in particular, this formula for the element that represents sort of the Dean twists, they provide a really absolutely concrete matrix realization of this representation of the mapping class group in this two-dimensional space, okay? And so as you can now probably imagine from the discussion this morning, this is a usually interesting problem. There's all sorts of multiplicities that can appear. It's very hard to compute, but what I show you is that these multiplicity spaces come somehow equipped with an action of this algebra of observables of Chern-Simons theory that we constructed in the first part. Let me give you another example, this time without puncture, but just handle. So let's say we take a genus 1 surface and no punctures. In this case, the representation space, as I said, the space of wave function is just G itself. And so you can work out how G decomposes with respect to the adjoint action of G on itself. And in fact, this is already in this GL11 example kind of interesting. Turns out that you get p squared minus 1 copies of these P0, this 4-dimensional projective cover that I discussed here with n equals 0, and then 2 copies of this irreducible 1-dimensional representation pi0, and a copy each of pi plus minus 1. Okay, so there are some things which are atypical irreducibles, and then some which are projective covers. I mean, most of them are projective covers, but these guys, although they could combine into projective cover, they don't. And so they are really irreducibles. So, so what you see from here is already, so now I said before, Chern-Simons observables act in multiplicity spaces. Now you see that this statement actually becomes more interesting. First, the P0, this projective cover, has a multiplicity space of p squared minus 1. So there's, in fact, an action of this algebra in this p squared minus 1-dimensional space. However, the pi0, which also sits at the bottom of the projective cover, P0, appears also here. So if you look at the multiplicity space of pi0, of the irreducible 1-dimensional representation pi0, it is actually p squared plus 1-dimensional. And so you get a representation of observables on this p squared plus 1-dimensional space. And so this is, of course, an indecomposable representation, which has a p squared minus 1-dimensional sub-representation. So you see the algebra of observables of Chern-Simons also has interesting indecomposable representations, which we can detect here. And of course, we can carry this to higher dimensions, sorry, higher genus. So it becomes more interesting if we go to higher genus. Now that should, I mean, so the purpose, maybe I'll summarize that later. So the purpose of this slide, was mostly to show you that this algebra of observables that we defined has actually, in this non-semi-simple context, very interesting representation theory. It acts on these multiplicity spaces somehow that we studied, or Torsten told us about this morning. But also it itself has indecomposable representations, just like the superalgebra. So it's a non-semi-simple algebra. So let me just mention quickly that you can then, as I said that before, you can use the general formula that I had on the few slides back. You can write to obtain to, I mean, use to write these elements that represent the Dehn-Twist generators. It's a very concrete formula that, I mean, you can easily work out matrix representations for. So for instance, we did this very explicitly for the torus. So as I just explained, in the torus case, one obtains a p squared plus 1-dimensional representation of the mapping class group of the torus, which is SL to Z. You can really look at obtain concrete matrix realization of that representation. If you're interested, you can look into our paper. You find explicit formulas for that. So that formula, in fact, in this case, deviates a little bit for those of you who have looked at this from the formula Saleur and Rosansky wrote like 30 years ago. It's closer to the one Mikhailov wrote in his work, but Mikhailov somehow used an overcomplete set of states, so that makes it a little difficult to work with his formulas. So somehow he has an action on a number of states which is larger than p squared plus 1. But if you kind of find all the linear dependencies, you can actually show that it also coincides with the formula that Mikhailov wrote. So of course, as I said, this is just one example, and it's very easy from this with this theory to work out these representations for arbitrary genus in any number of points. Okay, so I think that brings me to the end of the talk. In fact, 5 minutes late if I no, 5 minutes early, in fact. So let me just briefly summarize. I think the main message of this talk that you might want to take along, if you want to take anything along, is that I've showed you how to construct a very interesting family, multi-parameter family of algebras, which are somehow attached to surfaces, two-dimensional surfaces with handles and punctures. You can construct these for any Lie algebra, Lie superalgebra, and they come as functions of some deformation parameter Q or H bar. So I think the main message, of course, was, so large part of this is, of course, not new. And as long as we talk about this Lie superalgebras, this is an old construction, but the new message is that it actually goes through, if you know what you're doing, it goes through to the non-semi-simple or superalgebra case and gives really precise definitions of these algebras. And I've tried to convince you at the example of GL11 that these algebras are actually really interesting. They have a very interesting non-trivial ground state degeneracies, which have to do with this problem of decomposition of tensor products of representations or representations of, and of course, for the condensed matter enthusiasts, have to do with the sort of the ground state degeneracy of topological states of matter. And it also comes equipped with interesting representations of mapping class topological phases of matter that have to do with the construction of gates, and it's actually very important to control this construction. So with this, I think I've kind of brought the main messages home. I think there's many extensions, many relate to things also we heard in the last few days about extensions to sort of differential graded derived contexts. In particular, of course, other applications, straightforward extensions would be to develop this also for other supergroups like SL12 or PSO22, as you know, that's the ones that physicists can also do. And using all the technology that is available in mathematics, I think to some extent can also be extended beyond that. Again, refer to the talk this morning. And with that, I want to stop. Okay, thank you.
Thank you very much. Questions?
No, I have one. So I guess you give a nice explanation of how we can sort of think about this category, which is the representations of UQ of a particular superalgebra. And earlier we heard about these functors that go between representation categories of superalgebras that basically go by taking cohomology of some square zero odd element. And so I guess I wondered if those functors are sort of compatible with the Q deformation that you're using, and if there's a sense in which I could reduce, for example, the GLMN case to the smaller GLM-1N-1 case by doing something like that.
Yeah, I think that they are compatible with that. I mean, that would be sort of my
okay. Has there been a lot of work done on operations like that, or is that kind of?
It's a good question. I must say that myself, I only explored it in this in the undeformed context. So they probably, I guess nobody of the mathematicians is around. They would know. I can check. I'm not aware of.
I'd be curious.
Anything concrete I can give, but I would be surprised if this hasn't been explored.
Other questions?
And in fact, so some of the consequences of this for sure have been explored. I mean, there is, of course, so you can wonder, of course, to which extent you can get sort of new invariants, topological invariants from studying these super algebra representations, of which extent you just get sort of invariants for, when you start GLNM for GLN minus M, things of this type. And so depending on which observables you look at, some observables certainly can be just computed in GLN minus M, as we saw this morning.
Mm-hmm. Yeah, okay, is there any sort of general result about, so that this category is not semi-simple, but I guess I could take this sort of semi-simplification of it. Is it easy to say what that smaller or more simple category is in examples, or is there some sort of?
Yeah, it's another good question. Yeah, another good question to which unfortunately I don't have really an answer. I can see, of course, that that one can look at that for GL11. Yeah, I have to think about it. I mean, it would be interesting to.
Thank you so much.
To discuss it a little bit more. Sorry. Yep. Also, the question, so as I was asking, the question was about semi-simplification of these categories that are obtained in this Q-deformed context. Again, I feel that probably this has been discussed. It's more like my lack of knowledge about recent literature on these Q-deformed categories.
What can you say about other quantizations of Chern-Simons theory with the supergroup? I mean, you talked about this combinatorial quantization.
So you didn't get the full question. Other quantizations of
other quantizations of Chern-Simons theory with the supergroup. I mean, for example.
Yeah. So I said one thing I said already, right? I mean, if you look at, I mean, I think the most extensive concrete example were Mikhailov's work, in particular also his PhD thesis. He has representations. For instance, of mapping class group, and they are related modulo these small issues in the way he was writing it. The other thing that was also I kind of mentioned briefly, I mean I mentioned on the slide, but I think I didn't talk about it, is that of course there's a general scheme to kind of construct, for instance, mapping class group representations based on non-semi-simple categories or algebras. Due to Lubachenko and Majid, I think this is non-graded, but non-semi-simple. And in the cases where we have compared them, we got the same representations. I mean, we checked. So in this case, let me say that's a little different because now it sounds a bit funny. But for instance, for Lubachenko Majid, they say they have a representation of the modular group on the center of the Hopf algebra. And indeed, as you can see when you go through this, I mean, this P squared plus one-dimensional space is really the center. And when I look at their formula, how they write a representation of the modular group thereon, it actually can be shown to be unitarily equivalent to the formula I gave you. Okay. So I think, so of course, if we're non-semi-simple, yeah, then the situation is very well investigated. So we conjectured that, of course, we always get, I mean, in non-semi-simple, in some sense, we get like, in the semi-simple context, we got Rezhitikin to Rayev, the belief is for this mapping class group representations, we would get Lubachenko Majid representation of the mapping class group, and then, of course, an extension of that for the algebra of observables. So I don't think it's a sort of, this is not a complete answer, but it kind of suggests that it's not so far off from other quantization schemes.
What type of invariance of three manifolds or knots and links do you get from this?
I didn't get the question. What type of invariance?
Sorry, what type of invariance of three manifolds or knots and links do you get from the supergroups?
Again, got only to the invariance of three manifolds. So, I don't know. So, I mean, so initially, of course, when like in early 90s, I think the first work on this was Rosansky-Zaleur. It's still quite well known. So they constructed some kind of invariance of length spaces and ciphered fibered manifolds based on this GL11. So there is then there's of course extensions of this. So I'm not sure. Maybe I didn't.
Yeah, okay. Maybe you can hear me now. So
yeah. Okay.
No, thank you. That's okay. Thank you for reminding. So are there other questions? If not,
so if not, then maybe I can, as a final speaker, say a few words. Again, I know as also as an organizer that these days it's very difficult to organize meetings, hybrid meetings, because you never really know what's going to happen. So I'm really grateful for the organizers of this meeting that they followed through and actually eventually after I think 2 or 3 times reschedule went ahead and pushed this through. So thanks to Thomas, well, Terry, I haven't actually seen, but maybe he just and Johannes and Igmar for actually going through this, this and creating this meeting. I think it's even as an online participant at the hybrid meeting, I think it's very important to have these meetings because it kind of creates this creative randomness of listening into talks that you haven't actually put on your agenda like a week before. And so I'm really grateful that you went through, and I think it was really a very interesting meeting. Thanks a lot.
I think maybe also we should thank especially Simone for taking care of a lot of really the hard part of the local organization, and also Sebastian, who made the computers actually work in the way that they were supposed to. So
it's Sebastian and Lucas.
And Lucas, who's in Berlin. But
let's give them a round of applause. Laura, who took care of many other things. She's not here. She's with the kids. Okay. Well, thank you all for coming. And you know, doing all odds. I mean, I don't know. It was not impossible for anyone, you know, among you to come here. Not too difficult, I hope. Thank you for the online participants to for joining and also participating in this meeting. Yeah, we're very happy to have been able to do this, and we'll see how things develop in the future with these meetings and other meetings. Thank you all again, and have a good trip home for those who go home and hang around. So thank you very much again.
Okay, bye-bye.